the last class we started with looking at what is Dosy. This is an acronym for diffusion ordered spectroscopy, one of the very useful experiments in NMR, not only in drug discovery, but also for studying small molecule aggregation, proteins and etc. So, let us continue with that today. So, this is the picture which shows how this Dosy experiment, what kind of things are is used. So, the most important thing in Dosy is the use of gradients. So, we saw last class that gradients are basically coils which are present in the probe near the RF coils, and they work by circulating current in this coil, and that current generates a gradient in the vertical, in the center of the coil in the vertical direction. So, depending on the current, the direct movement of current, the direction of the current, the magnetic field can be either upwards or it can be downwards. So, typically what happens in all spectrometers, we have what is called Z gradients. So, we call it as GZ, and that generates current in these coils, and if you put it in one direction, it will be an upward field towards the B0, this is the main magnetic field, or if you do it in anti-clockwise or in a different direction, it will be in the negative direction. So, now imagine that you have a sample like this, and this is the what is called as effective RF coil volume, effective volume of the sample, because this is the volume which is basically seen by the RF coil. So, there will be sample above and below which is not available to the RF coil and the gradients. So, our focus will be only on this portion. So, this is typically 2 centimeters, 20 millimeters or 18 millimeters long. So, suppose we have a molecule which is at this end of the sample, and the same molecule, another copy of the molecule is sitting at the bottom of the sample. Now, when I apply this gradient, it experiences a different magnetic field. So, the molecule sitting here experiences B0 plus a certain field which depends on its z axis coordinate, meaning how far it is from the center. Now, the one which is at the bottom experiences a B0 minus this gradient into this coordinate, which is at the minus, that is coming from here, that this coil carries, that the bottom coil carries current which is opposite in direction compared to what is in the top. So, therefore, top and bottom oppose each other. So, typically the top portion will be along the magnetic field B0, and the bottom magnetic field generated will be opposing the main magnetic field. So, therefore, we can write the bottom part of the sample as B0 minus Gz and top part of the sample as B0 plus Gz. So, now remember, according to the standard NMR concept, that the precessional frequency, or we use the word Larmor precession, is defined by gamma into B0. But now, because of this additional magnetic field, for the top part of the sample, the molecule has B0 plus Gz, and for the bottom half part of the sample, it is B0 minus Gz. So, the same molecule, suppose let us say we are looking at water molecules or any molecule, the same molecule now has different precessional frequency along the sample. So, this is what the gradient does, it creates a linearly varying magnetic field across the sample. So, when I apply a pulse, the signal will first come to the xy plane. Now, because of the gradient, the different molecules will now start precessing not according to one frequency, but different frequencies, and these different frequencies have been created by this gradient, that because the same molecule which has all phased together now start dephasing at different speed, because each sample each molecule along this sample has different precessional frequency. So, you can also say that we have created an additional chemical shift along the sample. So, the same molecule now is spread over a large chemical shift range, because each part of this sample has different omega 0. So, therefore, the molecules do not go in phase, they start to dephase, similar to what you see in T2 relaxation. So, this is also similar to that, but this is now an induced kind of a dephasing and not a random dephasing which happens in the T2 case. So, therefore, this dephasing now continues, and after some time all the magnetization has fanned out in all the xy direction, because each molecule, you can see from here this end of the sample to this end of the sample, each of the spins or molecule have different omega 0. So, they go out of phase, they are not moving together and they become completely dephased. So, therefore, if we record a spectrum at this point, we will not get any signal from the sample, because you see the total vector addition of all the magnetization is now equal to 0. So, therefore, you apply a pulse, then you apply a gradient, then your signal is completely gone. And typically this gradient is applied for a very short duration. It is similar to the pulse, but pulse is about microsecond, gradients are about hundreds of microseconds, 100 or 500 or sometimes up to milliseconds. So, they are not very long, but at the same time they are short in time. So, we use the word gradient pulse. So, we say pulse field gradients. This is the typical terminology is used in when we describe gradients. So, now let us say how is all this connected to Dosy. Let us continue more. So, now suppose I have done this exercise, I have excited the magnetization, I have applied a gradient, and because of the gradient after some time the complete dephasing has taken place. Now, I can undo this, whatever I have done the dephasing by applying now a reverse gradient. So, now you can see here, if I apply a reverse gradient, now it is in the other way around. Here it was B0 plus Gz, now the top part of the sample becomes B0 minus Gz and the bottom part has plus Gz. So, you see now the precessional frequency has completely reversed. So, whatever was positive B0 plus Gz, now it is B0 minus Gz. So, that means if this vector, suppose this vector which is where I am pointing now, suppose it has moved by 40 degrees, because remember how is this degrees coming from? That degree is called phase, and the phase is nothing but omega into t. So, let me show that here. So, phase is equal to omega into t. So, after some time t, these phases have accumulated by each spin, and that phase depends on the magnetic field, because it depends on omega 0. So, now suppose this omega 0 for this sample has accumulated a phase of let us say 100 degrees, but when I apply now a reverse gradient, the same phase will go in the opposite direction, because now its frequency is minus this earlier frequency. Therefore, how much ever degree it has gone from this side, it will now go in the opposite direction. So, if I apply a reverse gradient for the same time t. So, suppose this gradient is time t and I apply the same time t, it will completely come back to the original position. So, all the spins here what you see here which have all got dephased, they have all dephased because they have gone by different angles, and the different angle is because they are along the different length part of the sample. So, because they are at the different part of the sample, they have experienced different omega zeros, but t is same for all, because this is the gradient time, that is same for all, but their omega zeros are different. So, their phases are all different, and because phases are all different, they underwent a complete dephasing. But now by applying this gradient, I can undo that by making now an opposite side. So, all these phases will be negative, because you can see here now they are subtracted and here it is added. So, they will come back to the go back by the same rotational angle. So, if something has moved by 50 degrees, will come back to minus 50 to 0. Similarly, something which has gone by 72 degrees will come back with minus 72 back to 0. So, all of them finally come back to the same position, and now they have come back in phase. So, this is the advantage of gradients, that you can dephase and rephase simply by applying a equal and opposite reverse. We use the word reverse, or you can say opposite gradient, and therefore, it has come back to the original phase. So, therefore, you can play around with magnetization by simply dephasing, rephasing, and whatever angle you want, you can choose that by applying this kind of gradients. So, what is basically the take home from this? The take home from this is we create a spatially varying magnetic field, and because of that each spins in the different parts of the sample now acquire different phases because they now have different frequencies. So, this phasing it results in each part of the sample is different phase. So, results in total dephasing which can be now reversed by applying a opposite gradient, which also creates a spatially varying field, but it is now undoing what was done before. So, how do you create a reverse gradient? Simply reverse the direction of the current which we saw in the previous slide. You apply the reverse direction and the gradient magnetic field is changed. Now, let us see how this helps in getting the Dosy experiment going. So, this is shown here. So, you can see in a Dosy what we do is the following. You first apply a gradient like we saw earlier. So, when you apply a gradient, now the molecules are all dephased because as we just discussed they are all in different locations. So, then what you do is you give some time. So, after applying a gradient you allow some time delay, means you do not do anything, just let the system idle. That delay is called delta, some delay delta. Now, during the delay delta the molecules are physically translating along the sample, they are diffusing because this is a random motion of the sample, random diffusional motion. So, the molecules are diffusing, that is a standard diffusion process. Now, because of this diffusion the molecules now are no longer in the same position. So, this molecule for example has moved from here at the top part of the sample, it has moved to the center. Similarly, one with the bottom part has moved towards the center. This is just an example which is shown, but you can imagine that for all molecules they are randomly moving around. So, they now start going to different locations. So, therefore, that depends on this value delta. If you give too much delay, too long delta, then molecules would have completely gone from one end of the sample to the second part of the sample, end of the sample. But if you give very short delay, they would not have moved at all. So, you see this short and long all depends on the diffusion rate. If the diffusion is slow, molecules even if you give long time they would not have moved. If the diffusion is fast, even if you give a short time they would have moved a lot. So, this relative terms on moving a lot, less short time and so on all depends on the diffusion coefficient of the molecule. So, now we do allow some delay. After this delay we now apply this reverse gradient. Okay. So, what do you expect? You expect that if I apply a forward gradient, that is normal gradient, and if I do a reverse I should get back to the original complete signal. Okay. But during that will not happen because of this delay here. Because of the delay the magnetizations have lost their original position. So, remember this dephasing rephasing works only because if they have not moved at all. So, if you recollect in the previous slide, so let us go back to the previous slide. Here we saw that this rephasing which is going from complete dephasing to original phasing, I mean original in phase happens only if the molecule has retained its original position, because whatever you see the term Z comes here. So, the omega naught depends very critically on the Z value, means how far it is from the origin. Suppose I put the origin as center, I can say this much is the distance or this down is distance. So, the phase it accumulates, the phase phi we saw that is equal to omega into t, but that phase will depend therefore on the Z value. So, if it has to rephase means it has to exactly come back to the original position, it should not move at all, because if it moves then this Z will be different from this Z here, the molecule will be at a different location. So, therefore, its phase will not be completely come back to original, it will continue to be slightly dephased. So, this perfect rephasing what is shown here therefore, will work only if the molecules have not moved from their position, means the molecule have not diffused. So, therefore, this gradient should be immediately applied as soon as you apply the first gradient, but in this in Dosy we give a delay, and because of this delay the molecules when they move they do not are located in the they are not located in the same locations. So, they do not completely rephase back, and this is exactly what we want. We do not want it to be rephased completely, because if it is rephased everything is back to the original position, that is not useful for us. What we want is some amount of dephasing because of diffusion, and that will give information on the diffusion process. So, let us see by vector picture what is happening. This is what we saw. If you have, let us say, 2 spins. So, I have put 2 arrows and this corresponds to these 2 spins. Then after the gradient is applied, suppose they are out of phase, means they are, one is exactly opposite to the other. So, there is no signal. If you add the 2 signal, it is opposite. So, it is 0. So, now when I apply the gradient delay, this phase does not change because molecules are moving, but the phase has nothing to do with the molecule movement, it is just remains like this. But now when I apply a reverse gradient, because the positions have changed, we can see here it is Z dash and Z double dash, means just saying that these 2 molecules are no longer at the same location or position as before. Because of this, when you do the undoing by reverse gradient, it does not bring them back in phase because they are no longer as the same position. So, this phase which was here perfect together is not together now. So, what is the consequence of this? The consequence of this is there is incomplete rephasing, and that consequence is there is a decrease in the intensity of the signal compared to the original signal. So, you can see this is the original signal, it is 100% phase. So, suppose it is 100 plus 100 200 or 10 x plus x 2x signal, if there is x is one signal, one spin, but here it is less than 2x, because if you have to take the component of this along x axis, remember always we take along one of the axis because the detector is sitting either along x or y. So, if you take along x axis, this is a component of this signal is less than the final original full signal. So, therefore, along x axis the signal has reduced, and along y axis anyway they cancel each other. So, signal intensity has now reduced, and this is exactly what we want. Because why do you want a decrease in signal? We want because we will understand how much diffusion has happened, and that should be proportional to the diffusion. If the diffusion is very fast, then the signal should be remain fully opposite to each other, they will completely be dephased. But if the diffusion is very slow, then the signal molecules would not have moved from here. So, they would be still close to their original locations, and the signal would still be very close to this full value. So, based on this we can figure out whether the diffusion has taken place or it has not taken place. In other words, what is the diffusion coefficient of the molecule. So, this is the flow chart. This is typically again what is done in Dosy. So, we first apply an RF pulse, then we then we dephase the magnetization by using a gradient, and this gradient when we to apply, we have to specify how the gradient is measured. So, gradient is measured by 2 parameters. One parameter is the strength of the gradient, how strong it is, and second is the duration, how long the gradient was applied. The product multiplication of these 2 gives you the total gradient strength. So, for example, I can reduce the gradient strength, I can increase delta, or I can increase gradient G, reduce delta. The product G into delta is what matters. Then after we apply the gradient, the molecules the spins have completely dephased, then I give a delta delay, a simple delay where nothing goes on, a simple system is completely at idle. Okay. During that process, during that delay, the molecule now undergoes translational diffusion movement. Then after this delay, we apply another gradient which is opposite to the first gradient, because we want to rephase the magnetization. Now, this rephase will work 100 perfectly if there has no diffusion, but because of diffusion during this delay delta, the magnetization is not completely rephased. So, therefore, the amount of decrease in the intensity I can measure by simply 2 experiments. One, I do not apply any delay and I apply a delay, or I keep the delay same, I simply in one experiment I do not apply a gradient, and another experiment I apply the gradient. So, when I do not apply the gradient, there is no question of dephasing. So, when there is no question of dephasing, there is no question of worrying about rephasing. So, the signal remains in phase throughout the experiment. That is my first point. but then if I switch on the gradient, then if I gradient is small, then the diffusion effect is less. So, I keep changing the gradient, the diffusion effects on the signal intensity will keep increasing. So, the experiment therefore involves changing the gradient strength. So, you record a series of experiment, not just one experiment. Dosy consists of a series, means a number of 1D. In each 1D spectrum you keep changing the gradient strength and start and look at the intensity, plot the intensity which should decrease as a function of the gradient strength. So, this is very much captured by the famous equation, the Stajal-Tanner equation relation, which gives you is derived way back in 60s, and that tells you this. It says that your original intensity where there was no gradient, which is the standard signal which we expect, now is attenuated, means decreased because of the application of this gradient and the delay, and that is given by this relation. So, in this relation what you can see, what are the parameters? D is the diffusion coefficient which we want to extract, which is what we want to find out. Delta is the delay, the diffusion delay which we gave, long delay here, and that is typically of the order of 100 or 200 or 300 milliseconds. That all depends on two factors. One is the how strong is the diffusion, and second what is the T1 relaxation of the sample or T2. This is the gradient strength. This is what we described, that this product G into delta come together. So, normally what we do is we keep the delta fixed, that means the duration of the gradient when during dephasing and rephasing, both the delta values are kept same and constant, and what is changed between experiments is this value of G. So, this whole experiment is carried out, and gamma is of course a constant, that is for hydrogen. So, the whole experiment is carried out by simply recording the spectrum at various G values. So, you keep G is 0, that is your first signal, then keep changing G to something else, then you get another signal which is called I. Like this you keep changing the G values and you monitor the I values. So, this can be plotted, now this is shown here. So, you can see this is the intensity, that I as a function of gradient delay strength, sorry, the gradient strength G value, this G value. So, if you plot this, you will see that you will get a curve like this. Why? Because this is like a Gaussian curve. So, this is half of a Gaussian. So, it looks like a Gaussian curve. So, in reality if you see, the spectrum will be like this. So, let us say this is a 1D spectrum of some molecule, and as you record the change the gradient, as you change the gradient you will see that the signal is decaying. Why is the signal is decreasing? Because as you increase the strength of the gradient, two things. One is you can notice from this equation that if I increase G value, my I should decrease. This is simply coming from the mathematical equation here. But if you want to understand intuitively what is going on, so what is going on is that when you increase the gradient, you dephase the signal a lot. So, if you want to rephase, you have to undo it, then undoing will work only if the diffusion has not taken place at all. But the moment diffusion is there, a small diffusion also will not allow you to undo or reverse the phasing of the signals which have got dephased. So, stronger the gradient, harder it is to rephase the signal which have got dephased. So, but of course, if the D is 0, suppose there is no diffusion at all, suppose imagine that you have some sample which has no diffusion, if D is 0, then the intensity should not change at all, the whole thing will be 0 and e to the power exponential of 0 is 1. So, I will always remain I 0. So, first if your D is not 0, then the amount of the signal which comes back because of the rephasing depends now on this G value. So, if I increase the G value, it becomes harder and harder to rephase them back and signal becomes lesser and lesser. Why does it become difficult to rephase them back? Because the small diffusion D, because of D, will change the phase values so much that rephasing will not help, because now the locations have changed. So, you need a very accurate repositioning for the rephasing. So, it will not rephase because the molecules have moved away. So, this is typically how the philosophy of great Dosy works as. So, let us say how does it manifest. So, what you do is how do you calculate the D value now. So, simply plot a equation, plot the picture function like this, and then you can fit this whole points to this equation, and from there the d value can be extracted. So, what is done is for each peak in the spectrum a d value is calculated. It is not that d is calculated for the whole molecule, d is actually calculated for each and every peak in the spectrum. So, if all the peaks belong to the same molecule, then obviously you will get the same d value for all the peaks, but you may have a mixture of molecules which have different d values. So, then the peaks corresponding to one molecule will show a different decay profile compared to the peaks belonging to the another molecule in the mixture, and this is the strength of Dosy. Dosy helps you now to differentiate between two peaks in the same spectrum that they do not belong to the same molecule. So, if you recollect, this was what we did with using Toxy, we identify spin system, but here the spin systems are different because the molecules are different. So, suppose imagine that these two are not the same molecule, these two peaks we are seeing here may not be the same molecule, then in that case if I extract the diffusion values, this whole series profile, we use the word profile, may correspond to a different d value because it is a different molecule, and similarly this whole profile may correspond to a different diffusion and it may be a different molecule. So, the Dosy spectrum is plotted like this. On the x axis you show the chemical shift value which is same as this 1D spectrum, and on the y axis you plot the diffusion value whose units is given like this. So, you can see that if you have two different mixture, two different molecules, from the 1D you cannot make out, of course unless you do a 2D will help you, but within from 1D you cannot make out that there are two molecules, but by simply doing this Dosy experiment you are able to now get them, and you can say that this is one molecule and this peak is belonging to another molecule, because if they were same molecule they should have been on the same line, means they should have the same d value, but the diffusion values are different and hence they can be called as different molecules. So, this is how the application of Dosy is. Dosy helps you to figure out that the mixture, the sample you can have may contain a mixture of different molecules, and this can be confirmed by Dosy. And if you are, let us say, looking at ligand protein interactions, what will happen is the ligand will have a particular mixture of ligand is given to you, okay, and you want to find out in that mixture which ligand binds to the protein, then you can use this Dosy, because in Dosy what will happen is all the small molecules will have the same diffusion values, but the one which binds to the protein will be slow diffusion, because it is now binding to the protein and it is behaving like a big molecule. It is bound to the protein, and protein is a large molecule. So, diffusion will be slow. So, and that ligand will have a smaller diffusion, slower diffusion or less d value. So, by that you can find out that that particular ligand is now binding to the protein, whereas the other is not binding, other ligands are not binding. So, this is a typical strategy followed when we try to screen a large number of compounds in drug discovery process, where the compounds are huge from a library of compounds, but the protein target is known. So, the goal is to find out which of this protein bind to the which of the ligands bind to the or molecules bind to the protein. This is also we use the word affinity NMR. Now, if the molecule is oligomerizing, let us say you are looking at some oligomerization process, for example, a molecule is becoming a dimer, a trimer or a tetramer and so on. So, as it starts oligomerizing, it becomes a bigger and bigger molecule, and therefore, its diffusion will start slowly reducing. So, by monitoring the diffusion coefficient like this, if you record the spectrum in real time as the process is happening in situ, then you will see the d value constantly will keep changing and the molecule will now show a shift along the time, or you can also do it for equilibrium. You do not have to do it as a kinetics experiment. You can also record slowly, and at each stage of oligomerization the d values will change, and that will be shift in the signal will be noticed. Now, according to the famous Stokes-Einstein equation, it says here that the d value is proportional to directly temperature and inversely proportional to the radius. So, this is the hydrodynamic radius of the molecule. So, that means when it oligomerizes, the hydrodynamic radius will change, and if that, let us say it changes, and then that will affect, it will reduce the diffusion value. So, and this is the viscosity of the sample. So, that means the diffusion also depends on viscosity. Larger the viscosity of a sample, if you have a viscous solution, the diffusion will be smaller, lesser. Similarly, if you increase temperature, diffusion will be faster. So, these are the different parameters which just determine what will be the d value. So, this Rs is the hydrodynamic radius, and that is now again remember is related to the molecular weight. So, higher the molecular weight, the diffusion will be less. So, typically if I double the molecular weight, I expect the diffusion to go down by half and so on. So, this d, and viscosity, if I double the viscosity, again d will go down. So, this completes the diffusion order spectroscopy Dosy. In the next class, we will take up the last topic of this course, which is very useful, again in use very routinely in drug discovery, and that is called saturation transfer difference, and we will see how that works.